Welcome to this video about my attempt to build an RC model of a SpaceX landing rocket. I was inspired by some big YouTubers like Tom Stanton or RC Test Flight to build something similar like this. They all had one thing in common. They used flaps to create the thrust vector control system. I wanted to have something different. I wanted to have the whole motor on a thrust vector control system. So I opened my CAD software and I started designing. The piece that you see me designing right here is the main spar of the thrust vector control system of my rocket. At the end of the designing process, I ended up with something that looked like this. You can see the second stage of the rocket here. In the second stage we have the battery bay where the lithium polymer battery goes into place, and underneath that we have 5 mounting holes for mounting a mini quad motor to the rocket. On the outside we have 4 mounting holes for the ESC in the flight controller stack. I am planning to have them on the inside in a future version for cooling, but right now it's on the outside for the accessibility of the micro USB port on the flight controller. You can see 2 holes here, one for getting the battery power to the ESC on the outside, and then from the ESC going to the motors, and from the flight controller to the servos. You can see these mounting holes here for mounting the second and first stage together. I am planning to have them either on the inside, or maybe I just put them together by duct tape in a future version, I don't know yet. Down here you can see the first stage. This is where the thrust vectoring happens. You can see I have 2 servos here for the roll axis, but in the building process I left this one away because I have only 4 outputs on the flight controller for outputting the PWM signal, and I need 2 for the motors and 1 for the roll, 1 for the pitch axis. So I can only have 1 here because they are opposite direction and I can't just connect them via a Y cable. But you can see the servo here is driving this bar here, and it is the roll direction of the motor. And if I fix that like this, you can see that I have here the pitch direction of the motor. Here on these 5 mounting holes, there goes this first motor into place, and it gets thrust vectored here. It can turn on both the roll and the pitch direction. You can see in this thing in here, we have another servo for controlling this direction. After I've exported the STL files from the CAD software, I imported them into my slicer software, and I placed them in the middle of the printing bed. I've changed the print setting until it looks something like this. So you can see the first stage here, and you can see the infill. It's the 3D honeycomb structure. It is very stable, but it is also very light. And you can see here I have made some solid layers, and up there you can see the 3D honeycomb infill. So I exported the G codes and got the files printed out. For tuning purposes, I went online and searched for a PID controller simulator. I found this Excel table, which is exactly that. You can see this is the graph of an almost perfect PID controller. The blue line represents the target value, and the red line represents the actual state of, in my case, the rocket. So you can see by increasing the mass here about 4 times, and I'm doing this because the rocket is very heavy compared to a quadcopter, which the INAV controller is supposed to keep up in the air. So I go ahead and make this 4 times larger, and so you can see the graph has changed. It isn't that good anymore. So you can see what I did is increasing the P gain, and you can see the actual line overshoots the target line and then bounces back, and you have these oscillations. Because this is just simulation, the real life rockets looked a bit different. So what you can see here, the first test of the rocket. When I gave throttle, it worked, but the oscillations quickly kept over and tipped the rocket over. So what I did is I further increased the P gain. You can see the graph has changed a bit, but more or less it's the same. It overshoots the target value and then bounces back, and you have the oscillations, and it should reach the target value behind here. You can see in the video it worked better, but the oscillation still kept on growing and tipped over the rocket. So what I did, I increased the D gain. And you can see the graph now, it is quite good. There is one overshooting, then it goes back, bounces back, but then it goes more or less straight, and it is very close to the blue line, how it should be, the target value. And so you can see this test, and you can see that it actually wasn't that bad. It flew stable for quite a few seconds. So what I further did is I detached it from the rubber ropes, and as you can see here, the rocket worked a bit, but the oscillations kept growing and growing, and finally they tipped over the rocket. So I increased the D value a bit more, and you can see in the graph here, this is a pretty good PID controller. You have one oscillation, one bounce back, but then it's more or less straight. And you can see that in the actual test, it flew for a few seconds, and I've had a more or less successful landing on the ground there. So it was controllable. And for the testing purposes with the prototype, this is good enough. And I will test it out and tune it more with the second prototype. Unfortunately, the video comes to an end here. If you liked this episode, please give it a thumbs up. And if you want to see the further development of the rocket and other upcoming projects, please click the subscribe button. Have a great day, and I'll see you next time.